Okay, we just have a couple more examples to run through in 10.2 before moving on. The first is an application problem where solving a triangle gives us a useful piece of information. So in many cases, when you're solving a triangle, if it's part of an application or a word problem, oftentimes there's only one part of that triangle that we actually want. So I've already worked out this problem in advance. I want to talk you through how using the law of cosines gets us a useful piece of information. So we're looking at an airplane that's flown 220 miles with a heading of 40 degrees, and then flies 180 miles with a heading of 170 degrees. And we're after that initial part of its journey. We're asked what the distance between the plane and its starting point is after those two stretches or distances it's traveled. So keyword here is the word heading. Heading is a navigational term, and what it means is it refers to a direction of travel. That direction is always given as an angle, and the way we interpret that is that this angle is measured clockwise from north. So you'll see in this diagram here, we're treating this as the starting point for the plane. And if north is given by this little arrow right here, then a heading of 40 degrees would be 40 degrees clockwise from that. So it's traveling this direction, 220 miles. Once it's reached this point here, after traveling those 220 miles, it changes course to a new heading of 170 degrees. So what I did is at this point I drew another arrow indicating north so I could measure that angle, 170 degrees clockwise from north. Now it's traveling this direction. This is not to scale. This line segment here actually should have been drawn a little bit shorter, but that's okay. It still depicts what we want to depict. We go 180 miles this direction, and at that point we want to measure the distance from where the plane is now to where the plane started. Now, in order to do that, you see I have a lot of other things written in here. I want to try and represent this triangle as an SAS, meaning a side, an angle, and a side. If I can do that, then the law of cosines can be used to solve this triangle, and this side of the triangle represents the distance that I'm looking for. So D is what I'm using as my label for distance here. We're going to attempt to solve that. So the issue is that even though I know these two sides, 220 miles, 180 miles, I'm not explicitly told this angle, but I am given enough information to find it. So if you look here, first of all, where I drew this arrow indicating north, if I extended that arrow down a little bit, then it creates a little bit more of that line segment that cuts this angle into two parts. This part right here is going to be 40 degrees, and that's because this angle is an alternate interior angle with this one. I can think of these two arrows as parallel lines since they both point north, and then this edge of the triangle, this leg of the triangle here, is going to be a transversal. These two angles would then be alternate interior angles. So that's a little bit from geometry, but we know that alternate interior angles are always congruent, meaning if this is 40 degrees, then this has to be 40 degrees. But that's only part of the angle in the triangle. I have this other part here, and to get that angle, I noticed that this 170 degree angle plus this piece right here should add up to 180 because it creates a straight line. That would imply that this piece of that angle is 10 degrees. So this angle that we need in the triangle is made up of two angles, one measuring 40 degrees, one measuring 10 degrees. That means this would be a 50 degree angle right here. So with that information, I notice that this is the angle that's opposite side D, so I can use the law of cosines to solve for D. D squared is equal to this side squared plus this side squared minus 2 times this side times times the cosine of that angle, 50 degrees. That's all that you're seeing written here. This goes into a calculator, and I get this really big number, which is supposed to be big because it's not the distance, it's D squared that I have. I would then need to take a square root of that answer, which in this case comes out to approximately 172.89 miles. Given the picture is not to scale, it still looks like a reasonable answer to get, looking at what the other side lengths of this triangle are. So that's basically all there is to it. We don't need these angles, so we don't need to solve the triangle completely. We just needed to do enough to get the distance that we were asked for in this problem. We're going to move up to one more application of the law of cosines, and for us it's not really even going to feel like an application of the law of cosines because you're not going to see the law of cosines explicitly used here. But what this is Heron's formula. So in section 10.1 we talked about an alternative area formula for a triangle that we came up with in terms of sine of an angle. Kind of used the law of sines. Here we're assuming that we have a triangle and it's an SSS triangle, meaning we know the three side lengths of the triangle, but we don't know any of the angles. It turns out that we can find the area of that triangle knowing only those three sides, and Heron's formula is the key to doing this. So in Heron's formula, you have this value S, which is called a semiperimeter. Semiperimeter is exactly half the perimeter of a triangle. So to find the semiperimeter, you add up all three sides, it gives you the perimeter, and then divide that by 2. We call that the semiperimeter. That quantity shows up 4 times in this formula. So the area of any triangle will be the square root of the semiperimeter S times S minus each of those sides individually. S minus A, S minus B, S minus C. That's 4 things that you multiply and then take the square root of. The reason this is showing up in this section, 10.2, is because if we were to prove Heron's formula, the standard proof uses the law of cosines, but it's a really messy and lengthy proof, and even though I have covered that proof when I've taught this class in the past, I realized it takes up so much time, it just wasn't really worth going through all of that. So if you're curious, you can look it up. The Wikipedia article for Heron's formula gives a full proof of that using the law of cosines. We're just going to use it, though. So I want to use Heron's formula to find the area of a triangle with the following 3 side lengths: 29.7, 42.3, 38.4, all measured in feet. So the very first thing you need to do is find S. Remember, that's the perimeter divided by 2. So we add up all 3 sides here, divide that by 2, and what we get is 55.2 feet. I'm just going to call it 55.2. Then we take that semiperimeter, that's S, and we need to subtract each side length from it to get these 3 values down here. So I did S minus A, 55.2 minus 29.7, that gives me 25.5. And then I do S minus B, I get 12.9. S minus C, that gives me 16.8. Heron's formula says take these 4 numbers that we found, multiply all 4 of them together, and then take the square root of that. That is going to give me the area of this triangle. So in this case, my area is coming out to 552.32 square feet because it's area. And that's it for 10.2.